Hello, please join me in this video where I am going to talk about the amine reactivities. Let us start with Hofmann elimination. How does Hofmann elimination work? Well, when we have an amine in the presence of excess alkyl halide, the amine undergoes excessive alkylation to form quaternary ammonium salt. The quaternary ammonium salt that has been formed can undergo elimination if we use a base. Now this base, the hydroxide, is generated from a reaction of silver oxide and water, which forms silver and the hydroxide. The silver captures the iodide and isolates it from the solution. Then the base is going to remove the proton from the more exposed position, the more exposed proton, and that leads to the formation of the less substituted product as the major compound. So remember, we could also remove the proton from here, and that would lead to the formation of Z-safe product. Now, in this case, the reaction favors the Hofmann elimination as opposed to the Z-safe product. So why does it favor the less substituted compound to form the Hofmann elimination product? Let us look at some of the stuff you learned before. We know that when you are doing an E2 elimination reaction, the leaving group and the proton being removed must be anti-coplanar. Okay? So if we want to align them properly, for example, we want to align this properly by looking at carbon C2 and C3. So we want to arrange the leaving group to be anti-coplanar with the proton that's being removed. So the leaving group is at the top on the side that's facing you. The proton here is at the bottom, but on the carbon that's facing away from you. Then we're going to end up with gauge interaction. This is not favorable. Gauge interaction implies that the compound is under steric hindrance, that is the steric strain. It does not like that. So if we look at it through carbon C2 and C1 and we try to do the same, so we align both the leaving group and the proton being removed to be anti-coplanar, then there's no gauge interaction. Okay, so the intermediate here is stable, but the product is the one which is less stable. So we can say the reaction is under kinetic control. Another reaction is the acylation of amine. Now, we mentioned earlier when we were doing aromatic reactions that aniline cannot undergo Friedel-Crafts reaction directly. We cannot do alkylation with aniline because the amine is nucleophilic. It's going to react with the Lewis compound to form a complex which renders the ring deactivated, so there's no more reaction. However, we can do protection. We can protect the amine. Once it is protected, then we can do the reaction. And then after that, we do the deprotection to achieve Friedel-Crafts alkylation. So here, to do the protection, we can use acid halide, or we can use acid anhydride, like acetic anhydride in this case. So when we're doing this reaction, you can use two equivalents of an amine, or if you use one equivalent of the acid halide, then you might need pyridine to capture the acid which is being formed. And then after that, we do the reaction, then deprotection. So this is a good method by which we can be able to do reactions in which amine causes some interference. The third type of reactions is what we call the diazonium salts. Azo means nitrogen, so diazonium salts are salts that contain nitrogen-nitrogen bond, okay, two nitrogen atoms. To form a diazonium salt, the primary amine reacts with nitrous acid, okay? Nitrous acid to form diazonium salt. The diazonium salt is stabilized by a halide. That halide could be bromide, could be chloride, could be iodide, okay? But the nitrous acid is usually unstable, so it needs to be prepared in situ. That is, through a reaction of sodium nitrite or potassium nitrite with an acid. So if we use sodium nitrite with hydrochloric acid, we can do a proton transfer to form the nitrous acid. The nitrous acid then undergoes a proton transfer, which leads to the elimination of water, and then we generate the nitrosonium ion. Nitrosonium ion is a strong electrophile, okay? So now the amine can react with nitrosonium ion, okay? So the amine attacks the nitrosonium ion in a nucleophilic attack, and the objective is to form the nitrogen-nitrogen triple bond. So once it attacks that, then we can do a proton transfer to remove that proton, and in the next step, our objective is to remove this oxygen, okay? So we are going to do a proton transfer, so we transform it into a group which is going to form a hydroxyl. So we do another proton transfer, and now we have the hydroxyl group, which we can protonate. So proton transfer, we protonate that, and then we do elimination to end up with the product, okay? Now, when you use a primary amine, primary amines that are not connected to an aromatic compound are not stable and are not of wide use. But if we do have an aryl group, an amine which is connected to aromatic compound, then the resulting diazonium salt is stabilized by resonance, and therefore we can use it to do a variety of reactions, because the diazo group which is attached is an excellent leaving group, because it can be kicked out as nitrogen gas, N2. So in other words, when we have a primary amine which is attached to an aromatic compound, we can be able to form an aryl diazonium salt. Once we form the aryl diazonium salt, then we can be able to perform a variety of reactions. For example, we can do what is called cyanation. We just use copper cyanide to install the cyanide group. We can use copper iodide to install an iodide. We can use bromination, copper bromide, to install a bromide. We can install a chloride. We can use fluoroboric acid to install fluorine here. We can use water and heat to install a hydroxyl group. We can also just do a reduction if we use the hypochlorous acid. And we can also do electrophilic aromatic substitution. Like if we have any aromatic compound, the aromatic compound is going to react with the diazonium salt, and we end up doing what is called azo coupling. So you can see all these reactions, we can achieve them once we form the diazonium salt. So in summary, we discussed how to do the synthesis of amines, reduction of a nitrile. We can do reduction of a nitro group. We can do reduction of primary amide, secondary amide, tertiary amide. We can do reduction of an azide, or we can use a bulky reagent to be able to perform alkylation of an amine. Then once we do alkylation, we can follow it with hydrolysis to form the primary amine, and we call that one Gabriel amine synthesis. We can do protection, then deprotection. We can do Hofmann elimination. We can do reductive amination to get us the product. and a variety of other reactions. So with that, thanks for watching. More information you can read in the notes, some of the mechanisms and some of the examples of other syntheses. Thank you for watching and have a good one.